they had to turn it off. Not because it malfunctioned, not because something went wrong with its instruments or its computers or its power systems, not because of a technical failure that engineers couldn't fix. They had to turn it off because it ran out of fuel, because it had been staring at the sky for 9.5 years, discovering things at a rate that nobody expected, finding planets by the thousands in a universe that was supposed to be mostly empty of them, and in doing so, transforming our understanding of the cosmos so fundamentally that the science community is still working through the implications. And what it found in those final months before NASA issued the shutdown command, on the 30th of October 2018, was in some ways the most disturbing thing of all. Not disturbing in a catastrophic sense. Disturbing in the way that a discovery is disturbing when it doesn't fit the models, when it doesn't match expectations, when it suggests that something is happening in the universe that our current theories can't fully explain. Disturbing in the way that the best discoveries always are, because they open questions faster than they close them. But to understand what Kepler found before they had to turn it off, you need to understand what Kepler was, what it was actually doing for those 9.5 years, what the act of staring at 150,000 stars simultaneously, measuring their brightness to a precision of parts per million, actually reveals about the nature of the galaxy we live in. Because the story of Kepler is not just the story of a telescope, it's the story of a revolution in how we understand our place in the cosmos, a revolution that happened not through a single dramatic discovery, but through the accumulation of thousands of data points, each one a tiny flicker of starlight, each one encoding the presence of a world orbiting another sun. The galaxy, it turns out, is full of planets. Overwhelmingly, astonishingly, almost incomprehensibly full of planets. And what that means for the question of life, for the question of how ordinary or extraordinary our solar system is, for the question of why the universe looks the way it does, is one of the most profound implications of any scientific instrument ever built. Let's start at the beginning. The Kepler Space Telescope was launched on the 6th of March, 2009. It was placed in an Earth-trailing heliocentric orbit, not an orbit around Earth, but orbiting the Sun, trailing behind Earth as Earth moves along its own orbit. This position was chosen deliberately to keep Kepler away from Earth's shadow and allow it to observe continuously, without interruption, for years at a time. Its mission was conceptually simple: stare at a fixed patch of sky, a region in the constellation Cygnus, and measure the brightness of roughly 150,000 stars simultaneously, continuously, with extraordinary precision. Every 30 minutes, it would read out the brightness of all 150,000 stars. Every 30 minutes, for years. The reason for this staring is the transit method of planet detection. When a planet orbits a star and its orbital plane is aligned with our line of sight, the planet periodically passes in front of the star transits it, blocking a small fraction of the star's light. The amount of dimming depends on the size of the planet relative to the star. For a Jupiter-sized planet transiting a Sun-like star, the dimming is about 1%. For an Earth-sized planet, the dimming is about 0.01%, 1 part in 10,000, 1 part in 10,000. To detect Earth-sized planets around Sun-like stars from space, you need to measure starlight with a precision better than 1 part in 10,000 from the ground. This is essentially impossible. Earth's atmosphere is turbulent, constantly distorting starlight, introducing noise that overwhelms the tiny signal of a transiting Earth-sized planet. From space, above the atmosphere, with a sufficiently stable spacecraft and sensitive detectors, it's extraordinarily difficult but achievable. Before Kepler launched, the technology had never been demonstrated at this level of precision. The Kepler mission was, in part, a test of whether the precision required to detect Earth-sized planets was achievable with real hardware in the real space environment. Some people in the planetary science community were skeptical. The precision was at the edge of what seemed physically possible. Kepler achieved it. And then some. The fundamental question that Kepler was designed to answer was this: how common are Earth-sized planets in the habitable zones of sun-like stars? Before Kepler, we had essentially no data on this. The planets detected before Kepler, primarily through the radial velocity method, which detects the slight wobble a planet induces in its host star's motion, were heavily biased toward large planets in tight orbits. Hot Jupiter's giant planets, orbiting extremely close to their stars, with orbital periods of days rather than years. These were easy to find. They produced large, easily detected signals. But they were almost certainly not representative of the general population of planets. The question of how many Earth-sized planets existed in habitable zones was a fundamental unknown. Estimates range from almost every star has one to they're extraordinarily rare. The answer had enormous implications for the search for life, for the probability of intelligent civilizations elsewhere in the galaxy, for whether the conditions that gave rise to life on Earth were typical or exceptional. Kepler was built to answer this question. Not from a handful of discoveries, but from statistics, from surveying 150,000 stars and asking, how often do planets of various sizes appear around stars of various types? What is the distribution of planet sizes, orbital periods, and host star characteristics? What fraction of sun-like stars have Earth-sized planets in habitable zones? What Kepler found over 9.5 years of continuous observation exceeded the most optimistic expectations. In its first 4 years of operation, its primary mission, Kepler discovered thousands of planet candidates. By the time the mission ended, the catalog contained more than 2,600 confirmed planets and nearly 2,000 additional candidates in a patch of sky roughly 10 degrees across a small fraction of the total celestial sphere. Kepler found more planets than had been discovered in the entire history of astronomy before Kepler launched. But the raw number of discoveries, dramatic as it is, understates the significance. What matters is what the numbers tell us about the underlying population. Kepler's statistical analysis, extrapolating from the fraction of stars with detected planets to the fraction with planets that Kepler couldn't detect because their orbital planes weren't aligned with our line of sight yields, a result that is, every time I think about it carefully, genuinely astonishing. Almost every star has planets. Not some stars, not most stars, almost every star. The Milky Way, with its 200 to 400 billion stars, contains hundreds of billions of planets. The average number of planets per star is approximately 1 or greater, meaning that for every star you look at in the night sky, there's almost certainly at least one planet orbiting it. Many stars have multiple planets. Our galaxy is not primarily a collection of stars with occasional planetary companions. It's a collection of planetary systems, each one centered on a star. This is so different from what astronomers assumed before the space age that it's worth pausing to appreciate the revision. For most of the history of science, planets, and by extension the possibility of life, were thought to be rare. The conditions required for planetary formation, for stable orbits, for liquid water, seem to demand such specific circumstances that each solar system was likely a unique accident. The Earth might be alone, or nearly alone in the galaxy. Kepler demolished this picture. The galaxy is not mostly empty, it's mostly full of planets, full of planetary systems, full of the kind of complexity that might, under the right circumstances, give rise to chemistry and biology and whatever comes after. Now let me tell you about the specific discoveries that I find most scientifically significant. Not the largest number of planets, not the most dramatic headlines, but the findings that most changed how planetary scientists think about the universe. The first is the discovery of super-Earths, a class of planet that doesn't exist in our solar system, but turns out to be extraordinarily common in the galaxy. Super-Earths are planets with masses and radii between Earth and Neptune, larger than Earth but smaller than Neptune, typically between 1.25 and 4 times Earth's radius. Before Kepler, the category barely existed as a concept. We had Earth, we had Neptune. The gap between them in our solar system was empty, no planets of intermediate size. Kepler found that this gap is filled in the galaxy at large. Super-Earths are the most common type of planet Kepler detected. They're everywhere, orbiting stars of every type at a wide range of orbital distances. The solar system, with its peculiar size distribution of planets, small rocky worlds in the inner system, giant gas and ice planets in the outer system, nothing in between turns out to be unusual. The galaxy's preferred planetary type is something our solar system doesn't have. This is remarkable. Our solar system was, for a long time, the only planetary system we knew in detail. We naturally assumed it was typical that the distribution of planet sizes we see here is representative of planetary systems in general. Kepler showed this assumption is wrong. Our solar system is a specific, unusual outcome of planet formation, not the generic result. What does this mean for habitability? Super-Earths are interesting targets in the search for life. Their larger masses mean stronger gravity, which might help retain atmospheres. Their larger sizes relative to Earth might mean more geological activity, more volcanic outgassing, more chemical diversity. Some of them, those in the right orbital range around the right kind of star, might have surface conditions compatible with liquid water. They might be among the most common habitable worlds in the galaxy, or they might not. Super-Earths might be water worlds, ocean planets, completely covered by deep global oceans, without the continent-ocean interface that may be important for Earth's carbon cycle and habitability. Or they might be too large for their surfaces to be geologically active in the right ways. The habitability of super-Earths is one of the most actively studied questions in exoplanet science, and Kepler's discovery of their prevalence has made it urgent. The second finding that I think deserves special emphasis is what's called the radius gap, or the Fulton gap, named after astronomer Benjamin Fulton, who identified it in 2017 using Kepler data. When Fulton and his collaborators looked at the distribution of planet radii in the Kepler sample, plotting the number of planets as a function of their size, they found something that had not been clearly visible in earlier analyses. There's a gap, a dip in the distribution. Planets with radii between about 1.5 and 2 times Earth's radius are noticeably rarer than planets just below or just above this range. This gap, the radius gap, is not random. It's a signature of a physical process. The most widely accepted explanation is photoevaporation. Close-in planets, those orbiting within about 100 days of their stars, are bombarded by the intense ultraviolet and X-ray radiation from their host star. This radiation heats the planet's atmosphere, causing it to expand and escape into space. Over millions to billions of years, a planet with a thick hydrogen-helium envelope can lose that envelope entirely if it's close enough to its star and its core isn't massive enough to retain it gravitationally. The radius gap marks the transition between two populations. Below the gap, rocky super-Earths planets that have lost their hydrogen-helium envelopes to photoevaporation, retaining only a thin atmosphere or none at all. Above the gap, sub-Neptunes, planets that retain their thick hydrogen-helium envelopes despite stellar radiation, either because they're farther from their star or because their cores are massive enough to hold on. The radius gap is physical forensics. It's the imprint of stellar radiation on planetary atmospheres, visible in the statistics of thousands of planetary systems, revealing the fundamental physical processes that determine what kinds of planets survive and in what forms. This matters for habitability because rocky planets below the gap are, in general, better candidates for Earth-like habitability than sub-Neptunes with thick hydrogen envelopes. The gap tells us which planets are rocky and which are not, and it tells us something about the history of those rocky planets, that they were once larger, that they lost their envelopes, that they survived a stripping process to become the bare, potentially rocky worlds we see today. The third finding, and the one that connects most directly to the headline of this video, is what Kepler observed when it looked at a star called KIC 8462852. You probably know this star by its nickname, Boyajian's star, named after astronomer Tabitha Boyajian, who led the paper reporting its bizarre behavior. In the popular press, it acquired another nickname, the alien megastructure star. Let me tell you what Kepler actually observed, and let me be precise, because the story is both genuinely mysterious and genuinely misrepresented in most popular accounts. KIC 8462852 is an F-type star, somewhat hotter and larger than the Sun, located about 1,470 light-years from Earth. In the Kepler data, most stars show brightness variations at the level of a few parts per million, tiny fluctuations from star spots and stellar oscillations. When a planet transits, you see a clean, symmetric dip with a specific depth, duration, and shape. That reveals the planet's size and orbital period. KIC 8462852 showed something completely different. Over the 4 years of Kepler's primary mission, KIC 8462852 showed multiple episodes of brightness dimming, not the regular, periodic, symmetric dips of a transiting planet, but irregular, asymmetric, complex brightness decreases of varying depth and duration. Some of these dips reduced the star's brightness by as much as 22%. Some lasted days, some weeks. They had complex shapes, not the clean U-shape of a planet transit, but complicated, irregular profiles suggesting multiple occulting objects of varying sizes and opacities moving in front of the star, a 22% dimming. Jupiter, the largest planet in our solar system, would block about 1% of the Sun's light during a transit. Whatever was blocking 22% of Boyajian's star's light was not a planet. It was something much larger, or much more opaque, or some complex collection of objects arranged in a non-planetary configuration. And there was more. Analysis of historical photographic plates, archival data going back to the early 20th century, suggested that Boyajian's star has been slowly, secularly dimming over the past century. Not just the sharp dips observed by Kepler, a gradual, long-term fading of the star's overall brightness. What causes this? What produces irregular, asymmetric brightness dips of up to 22% combined with long-term secular dimming in an otherwise ordinary F-type star? I want to go through the proposed explanations carefully because the history of how scientists have reasoned about Boyajian's star is as interesting as the phenomenon itself. The first explanation proposed, and the one that generated the extraordinary public attention, was advanced civilizations. An alien megastructure, specifically a Dyson swarm, a collection of vast artificial structures built by an advanced civilization to capture the star's energy, partially blocking its light in the complex, irregular way that Kepler observed. This is not as crazy as it sounds. As we discussed in our conversation about interstellar travel, a Type 2 civilization, one that has harnessed all the energy output of its host star, would require structures of stellar scale. A Dyson sphere, or more practically a Dyson swarm of individual collectors, would be exactly the kind of object that could produce the observed signature. The irregularity and asymmetry of the dips would reflect the specific arrangement of individual collectors, The secular dimming might reflect increasing construction over time. The alien megastructure hypothesis was never the leading scientific explanation. It was always the hypothesis of last resort, considered seriously only in the absence of a better natural explanation, because the history of astronomy is full of inexplicable observations that turned out to have mundane natural causes. The famous quip attributed to Carl Sagan, "Extraordinary claims require extraordinary evidence," applies with full force here. But it was considered, and the fact that it was considered that professional astronomers wrote papers exploring the possibility reflects the genuine strangeness of the Kepler data on this star. The alien megastructure hypothesis wasn't popular science fantasy. It was the logical endpoint of exhausting natural explanations. What are the natural explanations? Several have been proposed and investigated. The first was a swarm of comets, thousands or millions of comets in a highly elongated orbit, passing between us and the star in a dense cloud, absorbing and scattering its light. This explanation had some appeal. Comets are common in young planetary systems, and the irregular shapes and varying depths of the dips could be consistent with a complex, heterogeneous cloud of cometary material. The problems, the secular dimming is hard to explain by comets. Comets would produce a transient effect, not a century-long gradual fading. And the sheer amount of cometary material required enough to block 22% of the star's light strains credulity. You'd need an implausibly large number of comets, all mysteriously concentrated in a specific orbital configuration. The second explanation involves circumstellar dust, a disk or ring of dust surrounding the star, possibly the remnant of a planetary collision or the debris from a disrupted large body. Dust absorbs and scatters starlight, and an asymmetric, irregular dust structure could produce the complex dipping pattern. The secular dimming, the century-long fading, is actually consistent with the dust explanation. If a large planetary body was disrupted relatively recently, perhaps a few hundred years ago, the resulting debris cloud would gradually spread out and thin over time as it disperses around the star's orbit, explaining the long-term dimming. In 2018, a major breakthrough in understanding Boyajian's star came from an international campaign of multi-wavelength observations. When the star dimmed during one of the episodes of dipping that had been observed to occur roughly on a one-year time scale, astronomers monitored it simultaneously in ultraviolet, optical, and infrared light. The key diagnostic is this: if the occulting material is solid and opaque like a planet or a solid megastructure, it blocks all wavelengths of light equally. The dimming should be the same at ultraviolet, optical, and infrared wavelengths. If the material is dust, fine particles that scatter and absorb light, the dimming is wavelength dependent. Smaller particles scatter short wavelengths more effectively, so the star should appear dimmer in the ultraviolet than in the infrared during a dust occulting event. The 2018 observations found that the dimming is wavelength dependent. The star dims more in the ultraviolet than in the infrared. The occulting material is not solid and opaque, it's dust. This was a significant result. It ruled out solid megastructures. It strongly supported the dust hypothesis. The alien megastructure explanation, already the last resort, became essentially untenable, but it didn't fully solve the mystery. The dust explanation says the occulting material is dust. It doesn't tell you where the dust came from, why it's arranged in the specific complex pattern that produces the observed dips, or what disrupted event created it. The secular dimming remains puzzling. The timescale and magnitude are hard to reproduce with simple models. Boyajian's star is still not fully explained. It's the most unusual star in the Kepler dataset, unusual enough to have received more scientific attention than almost any other Kepler discovery, unusual enough to still be generating papers and observation campaigns. The alien megastructure hypothesis is effectively ruled out. The natural dust explanation is strongly supported, but the details, the origin of the dust, the mechanism producing the specific dipping pattern, the long-term dimming, remain active research questions. But here's something I want to say about Boyajian's star that often gets lost in the alien megastructure excitement. Even setting aside the exotic explanation, the phenomenon itself is genuinely scientifically valuable. We've never seen this kind of stellar variability before. We didn't know stars could behave this way, with this kind of complex, deep, irregular dimming produced by circumstellar material. The phenomenon, whatever its cause, is real. It's happening around a real star. And if it's happening around one star in the Kepler field, a field of 150,000 stars, there might be others like it that were missed, or might be discovered in future surveys. Understanding Boyajian's star fully, satisfyingly, mechanistically would tell us something about the late stages of planetary system evolution, about how planets are disrupted, how their material is distributed around the host star, how stellar radiation and orbital dynamics process this material over time. It would add a new chapter to our understanding of how planetary systems age. This is what unusual observations are for. Not to confirm existing models. Existing models, by definition, don't predict genuinely unusual things, but to point at processes that the models missed, to identify new physical mechanisms. To expand the space of what we know can happen, Kepler found Boyajian's star because it was watching, because it was staring continuously at 150,000 stars for years, measuring their brightness precisely enough to detect something as subtle as the secular dimming and as dramatic as the deep irregular dips. No previous telescope had the combination of precision, duration, and sample size to find this. Kepler was designed to find planets. It found something weirder. That's exploration. Let me now tell you about another class of discovery from the Kepler mission that I think is genuinely underappreciated in the public discussion. Something that doesn't generate alien megastructure headlines, but that is in many ways more scientifically profound. It's the discovery of the diversity of planetary system architectures. Before Kepler, our best model of a planetary system was our own inner rocky planets, asteroid belt, outer gas giants, outer ice giants. This is the template. This is what a planetary system looks like. Kepler has shown us that this template is one of many. That planetary systems come in extraordinary variety in the sizes, masses, compositions, and orbital arrangements of their planets. Some systems have multiple super-Earths packed into orbits that would all fit inside Mercury's orbit in our solar system, orbiting their stars with periods of days rather than years, in configurations that have no analog in our solar system. Some systems have planets in mean motion resonances, orbital period ratios of simple integers like 2:1 or 3:2 that preserve the memory of the system's migration history. Some systems have planets in extremely compact configurations where the mutual gravitational interactions between planets are measurable from Kepler's data, allowing mass determinations without radial velocity observations. And some systems are strikingly, almost uncomfortably Earth-like in their architecture. Kepler 452 system, for instance, a sun-like star with a planet orbiting at roughly the same distance as Earth, with a similar orbital period, with a size suggesting it's a rocky world or a water world. Not a perfect Earth analog Kepler. 452b is somewhat larger than Earth and its star is somewhat older, but close enough to be genuinely exciting. The diversity of planetary system architectures tells us something important about planetary formation. The process that forms planets is not highly deterministic. It doesn't always produce the same outcome. Small differences in initial conditions, in disk properties, in the timing of planet formation, in gravitational interactions between forming planets can produce wildly different outcomes. The solar system is one outcome. The compact systems of super-Earths are another. The hot Jupiter systems are another. Our solar system, with its particular architecture, is somewhere in the distribution, not at the center, not at a special location, but one specific outcome of a stochastic process that produces a wide variety of results. There's one more discovery from the Kepler mission that I want to spend time on because it's directly relevant to the question of life and has generated some of the most exciting and most contested science in the field. It's the discovery of the TRAPPIST, one system not by Kepler itself, but made famous by Kepler's follow-up observations and confirmed by the K2 mission, the extended Kepler mission, that operated after the failure of two of the spacecraft's four reaction wheels, which I'll describe in a moment. TRAPPIST-1 is an ultra-cool red dwarf star, one of the smallest and coolest stars known that still undergoes hydrogen fusion. It's located about 40 light years from Earth. In 2017, ground-based observations and Spitzer Space Telescope data revealed that TRAPPIST-1 hosts 7 Earth-sized planets, all of them roughly Earth-sized, all of them in orbits that would place them in or near the star's habitable zone. 7 Earth-sized planets. 3 of them, TRAPPIST, 1, E, F, and G, are considered the best candidates for habitability with estimated surface temperatures that might allow liquid water under the right atmospheric conditions. The TRAPPIST-1 system is the most extraordinary planetary system discovered since the space age began. 7 Earth-sized worlds around a single star. 3 of them potentially habitable, all within a relatively compact orbital configuration that allows them to interact gravitationally, affecting each other's orbits in ways that allow their masses to be precisely determined from transit timing variations. And the K2 mission, the extended Kepler mission, was critical in characterizing this system. By staring at TRAPPIST-1 for extended periods, K2 provided high-quality transit light curves for all 7 planets, allowing better determination of their sizes and orbital properties. The precision of Kepler-style photometry applied to TRAPPIST-1 transformed our understanding of this extraordinary system. What does TRAPPIST-1 mean for the search for life? As we discussed in our conversation about the James Webb Space Telescope, the TRAPPIST-1 planets are among the highest priority targets for atmospheric characterization. Webb has already begun observing them, trying to detect whether they have atmospheres, and if so, what those atmospheres are made of. The preliminary results are challenging and somewhat concerning for habitability, at least for the innermost planets, which appear to lack significant atmospheres. But the habitable zone planets E, F, and G are harder to characterize and have not yet revealed their atmospheric secrets. The investigation continues. Now let me tell you about the part of the Kepler story that I haven't yet described, the part that explains the headline, the part about why they had to turn it off. In May 2013, 4 years into the primary mission, Kepler lost the second of its 4 reaction wheels. Reaction wheels are spinning flywheels that maintain a spacecraft's pointing orientation. They're gyroscopes, allowing the spacecraft to point precisely at specific targets by spinning up or slowing down in response to control commands. Kepler needed 3 functioning reaction wheels to maintain the extraordinarily precise, stable pointing required to detect planet transits. With only 2 functioning reaction wheels, Kepler could no longer maintain the pointing stability of its primary mission. The science team faced a choice: end the mission or find a creative workaround. They found a workaround. Kepler's engineers realized that the spacecraft could use solar radiation pressure, the gentle but constant push of sunlight on the spacecraft's solar panels, as a 3rd reaction wheel. By orienting the spacecraft so that the solar panel faced the sun at a specific angle, the radiation pressure provided a stabilizing torque that, combined with the 2 remaining reaction wheels, allowed the spacecraft to maintain stable pointing along the plane of the ecliptic. This extended mission, called K2, had different observational properties from the primary mission. Instead of staring at one fixed field, K2 observed a series of fields along the ecliptic, spending roughly 80 days on each field before rotating to the next. This provided less continuous coverage of any individual star, but dramatically expanded the survey's sky-covered sampling stars in many different directions at different distances in different star-forming regions. K2 was remarkably productive. It discovered hundreds of additional exoplanets. It observed stars in young clusters, revealing how planetary systems look early in their formation. It characterized the TRAPPIST, one system. It discovered planets around nearby stars that are now targets for atmospheric characterization by Webb, but there was a cost. The K2 point and control, relying on solar radiation pressure, was less precise than the primary mission, and more importantly, the spacecraft's hydrazine fuel supply was finite. The reaction wheels required occasional momentum unloading, a process of firing small thrusters to counteract the angular momentum that had built up in the wheels. Every thruster firing used hydrazine, and the hydrazine was running out. By 2018, the fuel supply was critically low. In August 2018, during Kepler's final K2 campaign, NASA put the spacecraft into a hibernation state to preserve fuel for transmitting the final data set to Earth. The data was downloaded, and on the 30th of October 2018, NASA sent the retirement command. Kepler's tanks were empty. Its thrusters could no longer fire. It could no longer point. It could no longer observe. They had to turn it off. Not because it failed, not because its instruments stopped working, because it ran dry. Because 9.5 years of continuous observation had finally exhausted the fuel that kept it pointing at the sky. I want to close this first part with something that I think captures the full significance of what Kepler accomplished and why what it saw before they had to turn it off matters. In those final months of K2, those last observations before the fuel ran out, Kepler was doing something poignant. It was still finding planets, still staring at stars, still detecting the tiny dimmings of transiting worlds, still adding to the catalog of known planets around other suns. In its final campaign, Campaign 19, it observed for about a month before the fuel situation became critical. That last month of observation produced discoveries that are still being analyzed, and throughout the K2 mission, in the extended observations of various stellar fields, Kepler had accumulated evidence for something that had been hinted at in the primary mission but became clearer with the expanded sample. The planet occurrence rates around different types of stars are different. Red dwarf stars, the most common stars in the galaxy, have a higher occurrence rate of small planets than sun-like stars. The universe preferentially produces small rocky worlds around the most common type of star. This matters for the big picture. If small rocky planets are especially common around red dwarfs, and if red dwarfs make up 70% of all stars, then the most common habitable zone planets in the galaxy are orbiting red dwarfs, not sun-like stars. The search for life should perhaps focus more on red dwarf planets than on solar analogs. But there's a complication, the same complication we discussed in the context of TRAPPIST. One, red dwarfs are more magnetically active than sun-like stars. Their habitable zones are closer in. Their planets are tidally locked. Whether these factors make red dwarf planets less habitable, more habitable, or differently habitable is one of the central open questions in astrobiology. Kepler gave us the statistics. It told us how many planets of each type exist around each type of star. What it couldn't tell us, what no statistical survey of transits can tell us, is whether any of those planets are inhabited. That requires the next generation of telescopes the instruments that look at individual planets, read their atmospheric chemistry, search for the signatures of biology. Kepler opened the question. It showed us that the universe is full of candidates. It quantified the opportunity. What it found before they had to turn it off was, in the most precise sense, the shape of the question, how many worlds are out there? The answer, hundreds of billions in our galaxy alone, is the most important number in the search for life beyond Earth. Not the answer to the search. The scale of the opportunity. In part 2, I want to go deeper into what the Kepler catalog has revealed about the nature of planetary systems, about the specific architectures, the chemistry, the orbital dynamics, and into what the Boyajian star mystery tells us about phenomena in the galaxy that we didn't know existed. And I want to explore what comes after Kepler, the missions it inspired, the questions it handed off, and where the search for Earth 2 stands right now. Because Kepler had to turn off, but the search didn't. So we'd arrived at this place where Kepler has transformed our understanding of the galaxy, revealing that planets are everywhere, that super-Earths are the most common planetary type, that the radius gap tells us about atmospheric evolution, and that Boyajian star is doing something genuinely strange that we're still working to fully explain. The galaxy is full of worlds. The question is what those worlds are like. Now I want to go deeper into the specific physics that Kepler's discoveries have revealed about how planetary systems form and evolve, into what the Kepler catalog tells us about the conditions for habitability, and into what comes after Kepler, the missions and telescopes that are now carrying forward the questions it raised. But I want to start with something that I think is one of the most underappreciated results from the Kepler mission. Something that doesn't involve individual dramatic discoveries, but that emerges from the statistical analysis of the full catalog. Something about the architecture of planetary systems and what it tells us about the process of planet formation. When you look at the Kepler catalog as a whole, thousands of planetary systems, each characterized by the sizes and orbital periods of its planets, a specific pattern emerges. It's called peas in a pod. In multi-planet systems, systems where Kepler detected 2 or more planets, the planets within a single system tend to be similar to each other in size. If a system has one planet of about 1.5 Earth radii, its other planets are likely to also be around 1.5 Earth radii. If one planet is about 2.5 Earth radii, the others are too. The planets in a system are more similar to each other than they are to randomly chosen planets from other systems. The same pattern holds for orbital spacing. The gaps between planets in a multi-planet system, the ratios of adjacent orbital periods, tend to be regular and evenly spaced. Not perfectly regular, but more regular than random. This peas in a pod pattern is not what simple planet formation models predicted. Simple models generate a wide range of planet sizes and arbitrary orbital spacings within a single system. The regularity, the tendency of planets in the same system to be similar to each other, suggests that the formation process has a memory. That the properties of a planetary system are determined early by the properties of the protoplanetary disk from which the planets form, and that all the planets in a system inherit similar properties from that common origin. What determines the disk properties? The mass of the disk, its temperature structure, its composition, its turbulence. These properties vary from star to star, which is why different systems have different characteristic planet sizes. But within a single system, all planets form from the same disk and they all end up similar. The peas in a pod pattern is a fingerprint of the formation process. It says planetary systems are coherent. Their planets share a family resemblance determined by their common birthplace. And it has a specific implication for our solar system. Our solar system doesn't follow the peas in a pod pattern. Our inner planets are small and rocky. Our outer planets are giant. The range of planet sizes in our solar system, from Mercury at 0.38 Earth radii to Jupiter at 11.2 Earth radii, is vast. By Kepler's statistics, this kind of extreme size variation within a single system is unusual. Our solar system looks like an outlier, a system with unusually diverse planet sizes. Why is the solar system different? The leading explanation involves Jupiter. Jupiter's early formation and its subsequent migration inward and then outward through the protoplanetary disk disrupted the disk in ways that prevented the formation of super-Earths in the inner solar system. Jupiter essentially cleared the inner disk, creating the conditions for the smaller rocky planets we have. In most systems, no Jupiter-like disruptive giant formed, allowing the inner disk to produce the characteristic super-Earths and sub-Neptunes that Kepler finds everywhere. The solar system's peculiarity, its lack of super-Earths, its extreme size diversity, may be directly connected to Jupiter's existence. We have Jupiter. Jupiter affected our formation history. The result is a solar system that's unlike most of what Kepler found. This is humbling in the same way that previous astronomical revolutions were humbling. Copernicus showed us we're not at the center of the solar system. Hubble showed us we're not at the center of the galaxy. Kepler is showing us that our solar system is not the typical planetary system, that the configuration we evolved in is unusual, perhaps even rare, compared to the super-Earth-rich systems that dominate the galaxy's planetary population. Now let me talk about something that Kepler revealed about planetary composition that connects directly to the question of habitability, the volatile content of small planets. One of the most important questions about any potentially habitable planet is, does it have water? Water, as we've established in multiple conversations, is essential for life as we know it. Not just any water, liquid water, on the surface or in the interior, available for chemical reactions. The answer for a planet depends critically on its formation history. Whether a planet forms with significant water content and retains that water rather than losing it to space or sequestering it in its interior depends on where it formed in the protoplanetary disk, how the disk evolved, and what happened to the planet after it formed. The Kepler data, combined with mass measurements from radial velocity follow-up and from transit timing variations, has allowed planetary scientists to begin measuring the bulk densities of small planets. Density mass divided by volume tells you about composition. A planet with Earth's density is mostly rock and iron. A planet with half Earth's density has a significant fraction of lighter material, either a thick hydrogen-helium envelope or a large fraction of water or ice. What Kepler is finding is that small planets, the super-Earths and sub-Neptunes, show a wide range of densities. Some are as dense as iron, some are as light as water. The diversity in density reflects real diversity in composition. Some planets are predominantly rocky, others are water-rich, others have substantial gaseous envelopes. The water-rich planets, often called ocean worlds or water worlds, are particularly interesting. If a planet with several times Earth's mass has a significant water fraction, say 10 to 50% water by mass, it would have a global ocean of extraordinary depth, not Earth's ocean, which is a thin veneer covering about 71% of the surface to an average depth of about 3.7 kilometers. An ocean hundreds or thousands of kilometers deep, so deep that the pressure at the bottom would compress water into ice, even at high temperatures. Whether such deep ocean worlds are habitable is unclear. Earth's habitability involves a specific interplay between the ocean, the atmosphere, the land masses, and the geological cycling of carbon and other elements. A planet entirely covered by deep ocean would have different chemistry, different geology, different potentially problematic conditions for the origin and maintenance of life. The carbon cycle that stabilizes Earth's climate requires the interaction of ocean and land. A water world might not have this stabilizing mechanism, but the existence of water worlds, their prevalence in the Kepler catalog, expands the range of planetary types that might harbor life in some form. Even if surface ocean water worlds are not ideal for complex life, their deep interiors where warm water meets hot rock might harbor environments similar to Earth's hydrothermal vents. The same chemistry, the same energy gradients, the same conditions that support life in Earth's deep ocean floor environments might exist in the interiors of Kepler's water worlds. Now let me take you to something that connects Kepler's discoveries to one of the most active and consequential debates in exoplanet science. The question of what makes a habitable zone and whether the habitable zones of different types of stars are equally conducive to life. The habitable zone, the range of orbital distances where a planet's surface temperature allows liquid water, depends on both the star's luminosity and the planet's atmospheric properties. The classical habitable zone is defined for a planet with an Earth-like atmosphere and albedo. For a Sun-like star, this puts the habitable zone between roughly 0.95 and 1.7 AU. For a cooler, dimmer red dwarf, the habitable zone is much closer in perhaps 0.02 to 0.3 AU. Kepler's statistics allow us to calculate occurrence rates of habitable zone planets for different stellar types. The result is that habitable zone rocky planets are actually more common per star for red dwarfs than for Sun-like stars. The red dwarf habitable zone, while close in, is frequently populated with planets. The frequency of Earth-sized planets in the habitable zones of red dwarfs may be as high as 1 per star, meaning that the nearest red dwarf to our solar system might well have a habitable zone planet. Proxima Centauri, the nearest star to the Sun, 4.24 light-years away, is a red dwarf with a confirmed planet, Proxima b, in its habitable zone. This was not discovered by Kepler. It was found by radial velocity, but it's consistent with the statistical expectations from the Kepler survey. The implications are striking. If the nearest star has a habitable zone planet, and if red dwarfs, which host habitable zone planets at high frequency, make up 70% of all stars, then the closest habitable zone planet to Earth is almost certainly around a red dwarf. The statistical expectation is that there are about 40 to 50 potentially habitable red dwarf planets within just 20 light-years of Earth. But, and this is a substantial but habitable zone, doesn't mean habitable. Proximity to a red dwarf creates specific challenges. Tidal locking, as we've discussed. Intense stellar flares. A hard ultraviolet and X-ray radiation environment, especially when the star is young. Possible atmospheric stripping. Whether these challenges are overcome by specific planetary properties, sufficient magnetic fields, dense enough atmospheres, specific atmospheric chemistry is the core question in red dwarf exoplanet habitability. Kepler told us the planets are there. It could not tell us whether they're habitable. That requires spectroscopy, reading the atmospheric chemistry of individual planets, which is the job of the telescopes that followed Kepler. Let me now tell you about what came after Kepler, the missions it inspired and enabled, the telescopes that are now carrying forward the questions it raised. The immediate successor to Kepler's survey mission is TESS, the Transiting Exoplanet Survey Satellite, launched in April 2018, while Kepler was still operating in its final K2 campaign. TESS was designed to address one of Kepler's limitations. Kepler stared at one patch of sky, observing mostly distant stars. Its planet discoveries are mostly too far away for atmospheric characterization with current technology. TESS surveys the entire sky. It looks at 85% of the sky during its 2-year primary mission, observing stars that are, on average, much closer to Earth than Kepler's targets. The planets TESS finds orbit nearby stars, stars close enough that follow-up observations with ground-based and space-based telescopes can measure the planet's masses, characterize their atmospheres, and assess their habitability. TESS has been extraordinarily successful. As of this conversation, it has identified thousands of planet candidates and confirmed hundreds of planets. Its nearby targets include several high-priority atmospheric characterization targets, planets that Webb is now studying in detail. The partnership between TESS and Webb is one of the most productive relationships in current astronomy. TESS finds the planets. It identifies which nearby stars have transiting planets, determines the planet's sizes and orbital periods, and flags the most promising targets for atmospheric study. Webb then stares at those targets during transits, capturing the atmospheric transmission spectrum that reveals the planet's chemical composition. This is how we're going to answer the question of whether any of the thousands of planets Kepler found are inhabited. Not by Kepler itself, it wasn't designed for atmospheric characterization. By the combination of survey telescopes that find the planets and spectroscopic telescopes that read their atmospheres, Kepler was the first step. It proved that targets exist. It provided the statistics, the occurrence rates, the size distributions, the orbital architectures that tell us where to look and what to look for. Without Kepler, we wouldn't know which stars to point Webb at, or what size planets to prioritize, or what the expected frequency of habitable zone rocky planets is. Now I want to address something that came out of the Kepler data that has become increasingly important as we think about the search for intelligent life, something that connects the planet occurrence rates to the Fermi paradox in a specific quantitative way. The Fermi paradox, why is there no evidence of extraterrestrial intelligence in a universe full of stars and planets, can now be stated more precisely thanks to Kepler. Before Kepler, the number of potentially habitable planets was uncertain by many orders of magnitude. You could argue that Earth-sized planets in habitable zones were rare, and therefore the Fermi paradox was trivially resolved. There aren't many planets, so there aren't many intelligences. Kepler has closed off this escape route. Earth-sized planets in habitable zones are not rare. They're common. By the most conservative estimates, there are billions of potentially habitable zone rocky planets in the Milky Way alone. By more optimistic estimates, there might be tens of billions. This makes the Fermi paradox more acute. With billions of potentially habitable planets, many of them billions of years older than Earth, plenty of time for intelligent life to have evolved and spread across the galaxy, the silence of the cosmos becomes harder to explain. The possible explanations are the same, ones we've always had. Life itself might be rare. The origin of life from chemistry might be extraordinarily improbable, even given the right planetary conditions. Complex multicellular life might be extremely unlikely. The jump from microbes to multicellular organisms might require rare accidents. Intelligent life might be extremely unlikely. Technological civilization might be self-destructive. The distances between stars might be an insurmountable barrier. Or, most disturbing of all, there might be a great filter, something that nearly all technological civilizations encounter and fail to survive, and we haven't encountered it yet. What Kepler has done is remove planets are rare from the list of possible explanations for the Fermi paradox. That particular escape route is closed. The planets are there, billions of them. The silence requires a different explanation. This makes the search for life, and specifically the search for biosignatures in exoplanet atmospheres, more urgent, not less. If we detect life on a nearby world, even microbial life, it implies that life arises readily given the right conditions, which means the great filter, if it exists, is ahead of us, not behind us, which has profound and somewhat terrifying implications. If we detect nothing, if we search dozens or hundreds of nearby habitable zone planets and find no biosignatures, it implies that life is rare despite the planetary opportunities, which means the great filter might be behind us in the difficult transition from chemistry to biology, and were the rare exceptions that made it through. Both outcomes have enormous implications. Kepler set up the experiment. It found the planets. The search for biosignatures will complete it. Let me now return to Boyajian's star and tell you about something that happened in the years after the initial discovery that I think is both scientifically important and in a different way from the original mystery, genuinely unsettling. After the 2018 multi-wavelength observations confirmed that the occulting material is dust, not solid objects, astronomers began to look more carefully at what kind of dust. The wavelength-dependent dimming tells you about the size distribution of the dust particles. Detailed modeling of the spectral energy distribution during dimming events places constraints on the particle sizes, micron-scale dust, consistent with cometary or circumstellar disk material. But here's the interesting recent development. The secular dimming, the century-long gradual fading of Boyajian's star has been confirmed and extended using additional archival data. Not only has the star been slowly fading over the past century, but there appear to be patterns in the secular dimming that suggest it's not a simple monotonic decrease. There are fluctuations, periods of faster fading and slower fading, superimposed on the overall downward trend. This structure in the secular dimming suggests the dust causing it is not uniformly distributed. It's clumped, or it has a non-uniform spatial distribution around the star. Different amounts of dust pass in front of the star at different times as the material orbits, creating variations in the overall dimming rate. What disruption event produced this dust? The most quantitatively consistent explanation involves a planetary collision, a major impact between two planet-sized bodies in the Boyajian star system, occurring perhaps 200 to 300 years ago, based on the timescale of the secular dimming. Such a collision would have produced an enormous debris field, trillions of tons of fine dust that has been spreading around the star's orbit ever since. If this interpretation is correct, we're watching the aftermath of a planetary catastrophe. A collision between worlds, playing out in slow motion over centuries, its fingerprints visible in the light of the star from 1,470 light-years away. The dust that dims Boyajian's star is the pulverized remnants of worlds that no longer exist. This is sobering in a specific way. Planetary collisions are not hypothetical, they happen. Earth itself is thought to have formed partly through a giant impact, the Theia collision that created the moon. The late heavy bombardment that we discussed in the New Horizons conversation involved enormous numbers of collisions. Planetary systems are violent places, especially when young. Boyajian's star may be showing us what this violence looks like in another system. The debris of a collision that erased a world scattered its material around the star and left a fingerprint in the star's light that we can read from across the galaxy. The universe is not gentle. Planets form, and sometimes they're destroyed. The Kepler mission, in its 9.5 years of watching 150,000 stars, found not just the ordered, stable planetary systems we hope might harbor life, it also found the chaos, the disruption, the destruction. Now I want to address the question that I think is most important given everything Kepler revealed. Not how many planets are there, but what are the implications for finding life? The Kepler mission answered the question of planetary abundance with extraordinary thoroughness. Planets are everywhere. Habitable zone rocky planets are common. The conditions for life, liquid water, chemistry, stable temperatures, are potentially present in billions of locations in the galaxy. But Kepler was a blunt instrument for habitability assessment. It measured planet sizes and orbital periods. It could not measure atmospheric compositions, surface temperatures with precision, the presence of water, or any direct biosignature. It showed us that the opportunity exists, that there are billions of candidates without telling us whether any of them actually harbor life. The next question, and it's the question that the generation of telescopes after Kepler is designed to address, is given that the planets exist, do they have the specific properties required for habitability, atmospheres, liquid water, chemical conditions suitable for biology? This question is being addressed on multiple fronts. Webb, as I mentioned in the JWST conversation, is characterizing the atmospheres of the most accessible exoplanet targets, primarily super-Earths and sub-Neptunes around nearby red dwarfs. The TRAPPIST, one system, is a high priority. So are several planets discovered by TESS around the nearest stars. The results so far are intriguing, incomplete, and suggestive of a range of outcomes. Some planets appear to have atmospheres, others don't. Some show specific atmospheric features, others are harder to interpret. On the theoretical side, the Kepler statistics have enabled a new generation of habitability models. Instead of asking whether any individual planet might be habitable, scientists can now ask statistical questions given the distribution of planetary properties that Kepler has measured. What fraction of planets in various categories are likely to be habitable? What are the key parameters that distinguish habitable from non-habitable worlds? These models are suggesting that habitability might be sensitive to properties that Kepler couldn't measure: stellar activity levels, the presence of a large moon to stabilize axial tilt, the existence of plate tectonics, the specific chemical composition of the atmosphere. The peas in a pod regularity of planetary systems is encouraging if planets in a system are similar to each other, and if one is habitable, its neighbors might be too. But the diversity of system architecture suggests that habitability is not a guarantee, even for planets in the right orbital range. The honest state of play is this: Kepler told us there are billions of opportunities. The atmospheric characterization missions are now beginning to assess which opportunities are genuine. The biosignature search looking for chemical signatures of life in exoplanet atmospheres is in its earliest stages. We have not found life. We have not ruled it out. The search is on. And Kepler is why we know the scale of what we're searching. Let me close this second part with something about the legacy of the Kepler mission that goes beyond the science. Something about what it means for a civilization to build a telescope like Kepler and point it at the sky. Kepler was a statement that we take seriously the question of whether we're alone, that we're willing to invest hundreds of millions of dollars and thousands of person-years of scientific effort in the precise, patient, unglamorous work of staring at 150,000 stars for 9.5 years to find out how many have planets. The answer: almost every star has planets. Billions of potentially habitable worlds changes the context of the Fermi paradox from maybe planets are rare to planets are common. Why is the universe quiet? That shift has implications for how seriously we take the search for intelligence, how we think about our own fragility and resilience as a civilization, and what it would mean to find evidence of life elsewhere. Kepler ran until they had to turn it off, until the fuel was exhausted and the thrusters could no longer fire and the pointing could no longer be maintained. It worked until the last possible moment, and then a little longer, and then it was done. In its final transmissions, in the data that came back from those last days of observation before the retirement command, Kepler was still doing what it was built to do, still measuring the brightness of stars, still looking for the tiny dimmings of transiting worlds, still finding planets. They had to turn it off. But the knowledge, it gathered the catalog of thousands of worlds, the statistics of a galaxy full of planets, the discovery of super-Earths and the radius gap and Boyajian star. All of that survives. all of that is permanent. All of that is the foundation on which the search for life beyond Earth is now being built. In part 3, I want to close this story by asking what Kepler's full legacy means for the future of the search for life, for what the specific discoveries tell us about our place in the galaxy, and for what it means to live at this particular moment in history when we can finally, for the first time, begin to answer the question that humanity has been asking since we first looked up at the stars: are we alone? Kepler set up the experiment. The answer is coming. So we'd arrived at this place where Kepler's legacy is clear and profound. Planets are everywhere. The galaxy is full of them, billions of potentially habitable worlds orbiting stars of every type in configurations more diverse and more surprising than anyone expected. The question, are there planets, has been answered. The question, are any of them inhabited, is the one we're now equipped for the first time in history to seriously pursue. Now I want to bring this all the way home. To ask what it means, not just scientifically, but existentially, to live at the moment when we can finally begin to answer the oldest question humanity has ever asked. And to ask what the specific things Kepler found, the abundance of planets, the prevalence of super-Earths, the mystery of Boyajian's star, the silence of the Fermi paradox in a galaxy full of worlds, tell us about our situation and our future. Let me start with a question that I think reframes everything. Given that Kepler found so many planets, given that the galaxy is so clearly full of worlds, why haven't we found life yet? The honest answer is we haven't seriously looked yet. Not really. Not with instruments sensitive enough, not at enough targets, not for long enough. Let me be specific about what looking for life actually requires, because I think there's a common misconception that detecting biosignatures in exoplanet atmospheres is something we could easily do if we just tried hard enough. It's not. It's extraordinarily difficult, and we're at the very beginning of the capability to do it. When we look for life in an exoplanet atmosphere, we're looking for specific molecules: oxygen, methane, ozone, nitrous oxide, potentially dimethyl sulfide, that are produced by biological processes and would be present in quantities detectable from Earth orbit only if life is actively generating them at scale. The detection method is transmission spectroscopy, measuring how starlight is filtered through the planet's atmosphere during a transit, looking for the characteristic absorption features of specific molecules. The challenge is signal to noise. The transit signal of an Earth-sized planet around a sun-like star, the fractional dimming caused by the planet blocking starlight, is about 84 parts per million. The atmospheric signal, the additional dimming caused by molecules in the atmosphere absorbing specific wavelengths, is perhaps 1 to 10 parts per million on top of that. Detecting this with statistical confidence requires observing multiple transits, accumulating enough photons to beat down the noise. For TRAPPIST, a small red dwarf, where the planetary signals are larger because the star is so small, this is challenging, but approaching feasibility with Webb. Webb has now observed several TRAPPIST, planets during multiple transits, beginning to accumulate the signal needed to detect or rule out substantial atmospheres. The results so far suggest some planets lack thick atmospheres, while others remain ambiguous. For Earth-sized planets around sun-like stars, the most Earth-like configuration transmission spectroscopy is currently not feasible. The signals are too small. Webb is not sensitive enough. Detecting biosignatures in the atmosphere of an Earth analog around a sun-like star would require a telescope roughly 10 to 20 times larger than Webb, something like the proposed Habitable Worlds Observatory, a large UV optical infrared telescope specifically designed for this purpose. This telescope is in the concept phase. It's been identified as the top priority for the next flagship space mission in the most recent Astrophysics decadal survey. But it hasn't been funded, designed, or built yet. So the honest answer to why haven't we found life is we have found planets. We're beginning to characterize their atmospheres. We're not yet capable of detecting Earth-like biosignatures on truly Earth-like planets. The instruments capable of doing that are probably 15 to 20 years away. Kepler told us where to look. We're building the tools to actually look there. But there's a deeper layer to this question, and it connects to something I find genuinely important to think about carefully. Even if we build the Habitable Worlds Observatory, and even if it achieves its full capability, and even if we dedicate it entirely to searching for biosignatures on the most promising nearby Earth analogs, what's the realistic scope of what we can survey? The nearest Sun-like stars with potentially habitable planets are tens of light years away. The Habitable Worlds Observatory, as currently conceived, would be able to characterize the atmospheres of perhaps 20 to 50 of the most accessible targets nearby bright stars with detected Earth-sized planets in habitable zones. That's a sample. A meaningful sample, 20 to 50 worlds, is enough for statistical significance, but it's a tiny fraction of the billions of potentially habitable worlds that Kepler statistics imply exist in the galaxy. If we find biosignatures in several of those 20 to 50 targets, the implication is that life is common, that the galaxy is teeming with biology. If we find nothing in all 20 to 50, we need to be careful about the interpretation. The non-detection might mean life is rare, or it might mean that our sample was unlucky, or that biosignatures of life are harder to detect than we expected. The search is not a simple binary look and find or look and don't find. It's a statistical investigation with all the complexity and ambiguity that statistical investigations involve. The interpretation of the results will depend on the sample size, the sensitivity of the measurements, the specific targets chosen, and the theoretical models of what biosignatures from various types of life would look like. This is the mature, realistic picture of what the search for life beyond Earth actually looks like. Not a single dramatic discovery, though that's possible. More likely, a gradual accumulation of evidence, some planets with atmospheres, some without, some with chemical features that are ambiguous, some with features that are hard to explain without biology. The case for life or against it, building up over decades from hundreds of individual observations. Kepler prepared us for this by teaching us to think statistically, not about individual planets, but about populations, about occurrence rates, about what fraction of worlds in various categories have various properties. The search for life will require the same statistical thinking, not is this planet inhabited, but what fraction of planets like this one show biosignatures. Now let me tell you about something that has emerged from the Kepler data in recent years that I think is among the most scientifically significant results, and that gets less attention than it deserves because it doesn't have a catchy headline. It's the discovery of the relationship between stellar metallicity and planet type. Metallicity in the astronomical sense refers to the abundance of elements heavier than hydrogen and helium in a star. High metallicity stars have more iron, silicon, carbon, oxygen, and other elements. Low metallicity stars are mostly hydrogen and helium. The Kepler catalog, combined with spectroscopic measurements of host star metallicities, has revealed a pattern. Giant planets, hot Jupiters and warm Neptunes, preferentially orbit high metallicity stars. The more heavy elements in a star, the more likely it is to have a giant planet. But small planets, super-Earths, and sub-Neptunes show no such preference. They orbit stars across the full range of metallicities, low metallicity stars, high metallicity stars, and everything in between. Small planets are democratically distributed across stellar chemistry. What does this tell us? Giant planet formation requires large amounts of solid material in the protoplanetary disk-heavy elements to build the rocky or icy core that initiates gas accretion. More heavy elements in the star means more solid material available, means more likely giant planet formation. This is a clean physical story. Small planet formation is less sensitive to metallicity. Small planets can form from even relatively metal-poor disks because they require less solid material. This explains their more democratic distribution. The implication is profound. Low metallicity stars, which are, on average, older than high metallicity stars, because the galaxy's metallicity has been increasing over time. As stellar generations process hydrogen into heavier elements, are less likely to have giant planets, but just as likely to have small planets. The oldest stars in the galaxy, which have been around for 10 to 12 billion years, compared to the Sun's 4.6 billion, might well have small, rocky planets. Planets that have been orbiting their stars for twice as long as Earth has orbited the Sun. If life arises on planets, and if planets around old stars have had twice the time available for life to emerge and evolve, then the oldest planetary systems might harbor the most advanced life in the galaxy. Life that has had 10 billion years to evolve, compared to our 4 billion. Life that, if it developed technology, would have had 6 billion more years than us to spread through the galaxy. This is the context for the Fermi paradox in the light of Kepler's results. It's not just that the galaxy is full of planets. It's that some of those planets are twice as old as Earth. And the silence of the cosmos, the absence of any detectable signal from civilizations that would have had billions of years of head start, becomes, if anything, more puzzling. Either old civilizations don't exist, life doesn't persist long enough for technological development even over 10 billion years. Or they exist but don't produce signals we can detect they've gone quiet, or they communicate in ways we don't recognize, or they've transcended the kinds of technology that produce detectable electromagnetic emissions. Or there's something about the nature of technological civilization that prevents it from surviving long enough to spread across the galaxy. The Kepler data has made this puzzle sharper, not easier. The planets are there. The time is there. The silence persists. Let me now address something that I think is the deepest implication of Kepler's discovery of planetary abundance. Something that goes beyond the search for life and touches the most fundamental question about our place in the universe. We know now that Earth is not special in the sense of being one of only a few rocky worlds in the habitable zone of a star. There are billions of such worlds. The conditions that make Earth potentially habitable, right size, right orbit, right star type, are reproduced billions of times over in the galaxy. And yet, as far as we can tell, there's no other civilization we're aware of. No radio signal, no laser pulse, no megastructure, nothing that unambiguously says, here we are. This leads to a question that I think is both scientifically and philosophically important. Is Earth special, not in its physical configuration, not in having the conditions for life, but in having actually developed intelligent technological life? Is the emergence of intelligence after biology, after multicellular complexity, after neural architecture capable of abstract thought, extraordinarily improbable despite the abundance of suitable planetary environments? This is the crux of the rare Earth hypothesis, which we discussed in the context of Earth's rotation. The rare Earth argument says that while habitable zone rocky planets are common, the specific chain of events required for complex, intelligent life is rare. The right kind of moon, the right geological history. The right mass extinction events enough to drive evolution, not enough to end it. The right timing. The right sequence of evolutionary accidents. Kepler doesn't resolve this debate. What it does is separate the planetary abundance question from the intelligent life question. Before Kepler, you could argue that there weren't many planets, and therefore intelligence was rare simply because the environments were rare. Kepler closes off that argument. The environments exist. The planets are there. whether intelligence arises in those environments or whether it's an extraordinarily rare accident that happened once here in this particular history, is a separate question that planetary statistics alone cannot answer. The answer to that question, whether intelligence is common or rare in the galaxy, is the most important thing we could learn from the search for life beyond Earth. And Kepler, by establishing the planetary context, has made it possible for the first time to seriously pursue that answer. Let me now bring something forward that I think is underappreciated in discussions of Kepler's legacy. Its contribution to understanding stellar physics, something Kepler wasn't primarily designed for, but turned out to be extraordinarily useful for. Because Kepler was staring at 150,000 stars continuously for years, measuring their brightness with extraordinary precision. It was inadvertently building the most detailed data set of stellar variability ever assembled. Stars are not perfectly stable. They pulsate. They have star spots. They flicker and vary in complex ways that encode information about their internal structure and dynamics. The field of astroseismology, using stellar oscillations to probe stellar interiors, has been transformed by Kepler. The oscillations of a star are like the oscillations of a musical instrument. Their frequencies depend on the star's size, mass, temperature, and internal structure. By measuring these oscillations with Kepler's photometric precision, researchers can determine stellar ages, masses, and radii with unprecedented accuracy. This matters for exoplanets because the properties of a planet are always measured relative to its host star. If you know the star's radius precisely, you can determine the planet's radius precisely from the transit depth. If you know the star's age precisely, you know how long the planet has been orbiting it, which constrains its geological and atmospheric evolution. Kepler's astroseismology has improved our understanding of the Kepler planet host stars, which in turn has improved our understanding of the planets themselves. More broadly, Kepler's stellar physics results have contributed to our understanding of how stars evolve, how their activity levels change over time, how the rotation rates slow as they age, how star spot patterns affect stellar brightness. This knowledge is directly relevant to exoplanet habitability because stellar activity affects planetary atmospheres. A star that becomes less active as it ages provides a more stable environment for life on its planets to evolve over billions of years. The Sun's current low activity level compared to its more active youth has been good for Earth. The same transition from high to low activity is happening for billions of other stars. Understanding this transition, thanks in part to Kepler's stellar physics, is understanding part of the story of habitability across the galaxy. I want to tell you about one more result from Kepler that I find genuinely haunting. Not in a disturbing way, in the way that certain scientific results are haunting because they capture something profound about the nature of things. It's the discovery of disintegrating planets. In 2012, analysis of Kepler data revealed a bizarre class of object planets that appear to be actively evaporating. The light curves of these objects show asymmetric transits. The dimming before the planet crosses the star is different from the dimming after, and the transit shape is complex and variable from orbit to orbit. This asymmetry and variability is inconsistent with a solid, stable planetary body. It's consistent with a comet-like tail of dust and debris trailing behind the planet. These disintegrating planets are thought to be small, rocky worlds so close to their host stars that the stellar radiation is literally vaporizing the surface. The rock evaporates, condenses into dust particles as it expands away from the planet, and forms a trailing tail that absorbs and scatters starlight, creating the asymmetric transit signature. The planet is losing mass steadily, slowly, evaporating into space, and will eventually cease to exist. Several examples have been found all around small red dwarf stars, where the close-in habitable zones mean that rocky planets can end up in orbits so tight that they experience runaway surface evaporation. These disintegrating planets are scientifically valuable in a specific way. The dust they eject is the vaporized surface material, the rock and mineral content of the planet itself. By measuring the spectral absorption of this dust during transits, astronomers can determine the mineral composition of the planet's surface. They're literally reading the planet's crust from the dust of its destruction. The compositions that have been measured are consistent with rocky, silicate-rich material similar to Earth's surface, though with variations that reflect the specific geological history of each planet. We're reading the chemistry of other worlds from the dust of their disintegration. Forensic planetary science at stellar distances. But there's something else about disintegrating planets that I find profoundly moving. These are worlds in the process of ending. Not in a cosmic catastrophe, not a collision or a star-going supernova, but in a slow, patient, relentless evaporation. The star that gave the planet warmth for billions of years is also the agent of its destruction. The radiation that might once have sustained chemistry on the surface now vaporizes it. Every world has an end. Kepler found worlds in the process of ending and gave us a way to read their last chapters from across the galaxy. Now let me come to the final thing I want to say. The thing that I think is the deepest lesson of everything Kepler discovered. We live in a specific moment in history. A moment that is genuinely, objectively, historically unprecedented, not in the hyperbolic way that every generation says this about its own time, but in a precise, specific, factual sense. For all of human history, for the entire 300,000-year span of our species, we did not know whether there were other planets. We could see the stars. We could observe 5 of the planets in our solar system with the naked eye. Mercury, Venus, Mars, Jupiter, Saturn. We could infer from theoretical considerations that other stars might have planets too. But we didn't know. We had no data. We had no evidence one way or the other. This question, are there other worlds, was one of the oldest and most persistent in human thought. Philosophers debated it. Astronomers speculated about it. The Epicureans in ancient Greece argued for an infinite universe with infinite worlds. Giordano Bruno was burned at the stake in 1600, partly for arguing that the stars were other suns with their own planets. The question was contested, undecided, empirically inaccessible. Kepler answered it. In 9.5 years of staring at the sky, it transformed the question from unanswerable speculation to empirical fact. The answer is yes, other planets exist, billions of them. Almost every star has at least one. The universe is not a vast empty stage with our solar system as the only occupied set. It's full, overwhelmingly, astonishingly full of worlds. This is one of the most significant things any scientific instrument has ever determined, not the most precise measurement, not the most theoretically elegant result, but perhaps the most important single fact in terms of its implications for our understanding of our place in the cosmos that any telescope has ever established. And what does this mean? What does it mean to know that the universe is full of worlds? It means the question of life beyond Earth is not a philosophical speculation or a science fiction premise. It's a scientific question, a question with a specific, empirical, potentially answerable answer. A question that the instruments being built right now, Webb, TESS, the Roman Space Telescope, the Habitable Worlds Observatory, are designed to pursue. It means the Fermi paradox is not a puzzle about whether planets exist. It's a puzzle about something harder, about the prevalence of life, about the prevalence of intelligence, about the nature of technological civilization and its longevity. It means that Earth, a rocky world in the habitable zone of a G-type star, is one among billions, not unique in its physical configuration, potentially unique in having given rise to intelligence and consciousness and the capacity to ask these questions, but not unique in its planetary properties. and it means something about us, about what we are, about what it means to be the species that built Kepler, that was curious enough and patient enough and technically capable enough to stare at 150,000 stars for 9.5 years to find out if they had planets. They did. They do. The universe is full of them. They had to turn Kepler off. But the knowledge it gathered is permanent. The catalog of thousands of worlds, the statistics of planetary abundance, the understanding of planetary system architectures, all of this is now part of what humanity knows about the universe. Part of the permanent record of what we've understood. And the search, it enabled the search for biosignatures on those worlds. The search for life in a galaxy we now know is full of planets. That search is just beginning. We have the map now. Kepler gave us the map. We know where the planets are, roughly how many there are, what kinds are most common. What we don't know yet is whether any of them are home to something that, like us, is looking back. That's the question for the next generation of telescopes, for the next generation of scientists, for the next chapter of the story that Kepler started. There's something out there. They had to turn it off before it could tell us exactly what, but it told us enough. It told us the universe is full of worlds. Now we go look at them, and whatever we find life, or the absence of life, or something we haven't imagined yet, it will be the most important thing humanity has ever learned. Kepler made that possible. 9.5 years of patient, precise, continuous staring at the sky. 300,000 years of wondering if we're alone. And now, finally, we have the tools to find out. The search is on.
Imagine standing at a moment in history when scientists were surrounded by unanswered questions, questions so simple in appearance, yet so profound in meaning. One of those questions was this: what truly connects electricity and magnetism? People had already observed sparks, currents, and magnetic needles responding to wires, but the deeper relationship remained unclear. There was a mystery hidden in plain sight, and it revolved around one powerful idea: the behavior of moving electric charge. At first, electricity and magnetism seemed like separate phenomena. Electricity was associated with charges, sparks, and currents flowing through wires. Magnetism, on the other hand, was linked to magnets, compasses, and invisible fields that could pull or push objects without contact. Scientists knew these forces existed, but they didn't fully understand how tightly they were connected. It was like having two pieces of a puzzle without realizing they were part of the same picture. The turning point began when experiments showed that an electric current flowing through a wire could deflect a nearby compass needle. This suggested that electricity in motion had something to do with magnetism, but this discovery opened up even more questions. Was it only electric current in wires that created magnetic effects, or was there a deeper, more universal principle at work? To understand the mystery, we need to think about what an electric current really is. At its core, a current is simply a flow of electric charges, usually electrons, moving through a conductor. If moving charges create magnetism, then perhaps magnetism is not a separate force at all, but a natural consequence of motion. This idea sounds simple today, but at the time it was revolutionary. Scientists began to suspect that motion itself might be the key. Not just any motion, but the motion of electric charge. If a charge sits still, it creates an electric field. But if that same charge moves, could it also create a magnetic field? This question became one of the most important puzzles in physics. The challenge was not just to think about this idea, but to prove it. Science demands evidence, not just imagination. And the difficulty was enormous. The effects of moving charges can be incredibly small, especially when the motion is not part of a strong current. Detecting such tiny magnetic fields required precision beyond what most experiments of the time could achieve. This is where the story becomes fascinating. Scientists were not just exploring ideas. They were pushing the limits of measurement itself. They needed instruments sensitive enough to detect forces that were nearly invisible. They needed to eliminate errors, reduce noise, and ensure that what they observed was real and not an illusion. The mystery of moving charge and magnetism was not just about discovering a new fact. It was about changing how we understand